All right. Today we are going to start learning the differentiation rules. So we've learned how to take a derivative. We've done it the long way with the definition of derivative. Now we're going to learn how to do it the fast way. All right. So the first rule that you're going to learn about is called the power rule. So anything that is raised to an exponent, you can take the derivative using this rule. There are many things that don't look like they're in power rule form, but if you do a little bit of rewriting, you can get them in that form. All right, so here's how the power rule works. This is how another way to write derivative. I think I told you all about this on the first day. Derivative of the function with respect to x is how that would be properly said. We just say this is the derivative of x to the n power. All right, so here's how the power rule works. You multiply by the exponent. So we pull the exponent to the front. Our base stays the same. And then we subtract 1 from the exponent. So n times x to the n minus 1. That's it. That's how the power rule works. All right, so we're going to do a couple examples here. If you feel confident enough to use the power rule on your own, just based on that, try all these on your own. See how you do, especially like A and E. I think you can definitely do those on your own right now. The other ones may take a little bit of work, but try them out and then unpause the video and see how you did. All right, so for letter A, we have our exponent of 3, so we're going to multiply by the exponent, keep our base the same, and we're going to subtract 1 from the exponent. Simple as that, 3x squared. All right, I'm going to skip down to letter E. So even if there's a number in front, you just multiply by the exponent. So multiply by 3, you get 15x, and then you subtract 1 from the exponent, 15x squared. All right, the other three, slightly more challenging just because they're kind of hidden. But hopefully you remember from your previous classes, the square root is the same thing as a 1/2 power. So we can rewrite that as x to the 1/2 power and then apply our power rule that we've just learned about. So multiply by 1/2, keep the base the same, and then we're subtracting 1. So it's 1/2 minus 1. All right, well, that is 1/2 x to the negative 1/2. 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. All right, I skipped over the instructions here, but do not leave negative exponents or complex fractions. There's just kind of a general rule about our derivatives. We don't want to ever have negative exponents or complex fractions. So the way you get rid of a negative exponent is by putting it on the denominator. 1 over 2x to the 1/2. Okay, this is a perfectly good way to write your answer. If you like square roots better, you can change that back into a square root and write it like this. All right, either way is acceptable. Okay, I will say that this one is worth memorizing because we see it so much. All right, memorizing that the square root of x, the derivative is 1 over 2 square root of x. Okay, and that'll just make your life easier going forward if you memorize that one. You don't have to memorize it because you can go through the process every time, and it's not that long of a process, but it is helpful if you just memorize that one. All right, next one. This also doesn't look like it's in power rule form because power rule has to be a base raised to a power. That's it. You can't have it be on the denominator or multiplied by something else unless it's a constant multiplied. So this one, we have a problem because it's in the denominator, but we can fix that pretty quickly by doing the opposite of what I just did here. I had a negative exponent, so I put it on the bottom. Well, if it's on the bottom, I can pull it up to the top, and I can make it a negative exponent. So that's t to the negative 4. Then we apply our power rule. So we multiply by negative 4, keep our base the same, and we subtract 1, negative 4 minus 1. All right, well, that is negative 4t to the negative 5 power. And then we're not allowed to leave negative exponents, so we're going to put that t to the negative 5 back on the bottom. A lot of people make a mistake here. They think the negative 4 goes with it down to the bottom. The negative 4 does not. Negative 4 has its own exponent, actually. Its exponent is a positive 1. So because that has a positive exponent, it's going to stay right where it is, and only the t to the negative 5 moves down, and it turns into t to the 5th power on the bottom. All right, D. This is just a rule you're going to learn. We're going to write it in a box right below here in a second. But if you want to think of this as a power rule, if you don't have a variable, then you can always put one there. And this is, we want to multiply by 1. 5 times 1 is still 5. And so the exponent you would raise it to, so it's equal to 1, is a 0. Anything raised to the 0 power is 1. So then if you apply the power rule, you multiply by 0 times 5x, and then you would do 0 minus 1 here, but it actually doesn't matter now because everything's multiplied by 0, so that's equal to 0. All right, so just in the future, if you take the derivative of a constant, the derivative of a constant is 0. All right, that's just a rule you can memorize as well. All right, so like I said, that is this rule. Derivative of a constant, the derivative of a constant is equal to 0. The constant multiple rule, so that's this one that we did on part E right here. You can pull the constant out, do the derivative, and then put it back in. So that would be like this. You would have c multiplied by nx to the n minus 1, and then you multiply the c and n together, which is what we did. So we had 5. If we wrote out the steps, I didn't have us write out the steps here, but we had our 5 times and then our 3x squared, and then we multiplied our 5 and 3 together to get our 15. All right, sums and differences. Remember that derivatives are limits. We just went through our unit where we did the definition of derivative as a limit. And so a lot of the properties of limits work for derivatives too. Now, not every single one. You'll see that we're only talking about sums and differences here. We are not talking about products and quotients. Products and quotients have a whole other thing we have to do for derivatives, which we'll get to very soon. Okay, so you only want to do this if it's a sum or a difference. So if you have the sum of two functions or the difference of two functions or even more than two functions, you can separate them into individual derivatives. So you can take a derivative of f of x by itself plus the derivative of g of x by itself. Same thing for a difference. Derivative of f of x minus the derivative of g of x. All right, so that rule, those rules right there are super useful for taking the derivative of polynomials. So like this next example that we have down here. Okay, so I would never have you write this out every single problem. All right, we're just doing it this first time for our first example. Okay, but what's happening here is I want to take the derivative of f of x. All right, and f of x has 4 terms. So what that would be is we would do the derivative of the first term, 4x cubed, minus the derivative of the second term, 5x squared, plus the derivative of the third term, 7x, plus the derivative of the fourth term, 3. Okay, now you're never going to write it out like that. All right, just know that all you have to do is take the derivative of each term individually, and then whatever the answers are, you add or subtract them back together, and that's the answer. Okay, so the derivative of 4x cubed, we multiply by 3, that's 12x. We subtract 1 from the exponent, 12x squared. Second term, multiply by 2, that's negative 10. Subtract 1 from the exponent, so that's x to the first power. We don't need to write a 1 there. All right, 7x. If you take the derivative of 7x, x to the first power, you just get the constant in front, the coefficient, I should say. So that's plus 7. All right, you can think of it as we're multiplying by 1. So that's how we get the 7. And then 1 minus 1 is 0. X to the 0 is 1. So it's 7 times 1. We just need to write the 7. And then derivative of constant is equal to 0. So we don't need to write anything for that. So this is it. F prime of x is equal to 12x squared minus 10x plus 7. All right, next one. So this is, we have a quotient. So remember, there is no quotient rule written up here. All right, there is a quotient rule, but we haven't learned it yet. All right, so we have to get this out of this form, kind of similar to how the 1 over t to the fourth. We could not do that one until we wrote it like this. Okay, same idea here. This x is a common denominator to all 3 terms. Okay, so if we can just divide that out, we get 5x to the fourth. We can divide this right here, and we get minus 3x cubed. And then we can't divide this, but it's on the denominator. So just like with the t to the fourth, we're going to move it up to the numerator, plus 4x. And when we move it up to the numerator, it gets a negative exponent like that. All right, I encourage you to try the derivative itself on your own, and then unpause the video and see how you did on that one. All right, so first two are pretty standard. You just multiply by 4, subtract 1 from the exponent, multiply by 3, subtract 1 from the exponent. So it's a little tougher. You multiply by negative 1, so I get negative 4x, and then subtract 1, and you get negative 2. And then just like with the t up there, we can't leave our negative exponent, so we get 20x cubed minus 9x squared minus 4 divided by x squared. That would be our derivative right there. All right, let's flip it over on the back and kind of do a couple applications that we can do with our derivative. So use the graph to estimate the slope of the tangent line to y equals 2x to the 2/3 at 1, 1. Then verify your answer analytically. All right. All right. Had to go to lunch, but I'm back now. So we're going to use this graph to estimate our slope at 1, 1. And so they've drawn in the tangent line for us. And so we're just going to try to grab a couple points from this tangent line. We know that 1, 1 is one of those points. And so I'm just going to try to identify, a little tough here. We don't have any good ones. Let's just try to go here. And I'm going to say maybe that's like a third. That seems good to me. So 0, 1/3, and 1, 1. And we're just going to do an algebra 1 style slope between those. All right, so I get 1 minus 1/3 divided by 1 minus 0. That's equal to 2/3. Divided by 1 is 2/3. All right, so this is our estimate. So slope of the tangent line to y, so this is approximately equal to y prime of 1, which would be the slope of the tangent line at x equals 1. All right, now we're going to use our derivative rules we learned today to do it analytically. Analytically just means with algebra. All right, so we're going to take the derivative of our function, y prime is equal to, multiply by the exponent, 2/3, keep the base, subtract 1, 2/3, minus 1. Okay, so this is 2/3 x to the 2/3 minus 3/3, which is 1. And so we get 2/3 x to the negative 1/3, 2 minus 3. All right, and then no negative exponents, so keep the 2 on top, 3 on bottom, and move your x to the 1/3 to the bottom. All right, so this is the derivative, and then now we're going to plug in 1 and find y prime of 1. Okay, so that's 2 over 3 times 1 to the 1/3. And look at that, our estimate was exactly correct. The derivative is 2/3. So that is the slope of that line, 2 over 3. All right, find the derivative of this equation and write the equation of the tangent line to the curve at the point 1, 7. Leave your equation in point slope form. Okay, so we've done this a couple times now, point slope form. Okay, and on your pink sheet, that's your stuff you must know cold, we've written the point slope form in calculus. So I'm going to write it again for our notes here. Y minus f of a. Let me use the language of this problem. We don't have a function called f here, but we have a function called y. So I'm going to put y of a is equal to y prime of a multiplied by x minus a. Okay, in this problem, a is equal to 1. So that means that y of a is equal to 7. They've already given us the point. So the only thing we have left to find is the slope, y prime of a. So we need to take the derivative of this, y prime is equal to 6x plus 5. And then we plug in a, which is 1. So y prime of 1 is equal to 6 plus 5, which is 11. Plug everything in, and we're done. Y minus 7 is equal to 11 times x minus 1. And we leave it there. This is like a safe stopping place. We don't want to go to slope-intercept form unless it's a multiple choice question and it's forcing us to do that. Okay, any free response, you're just going to leave it there. All right, so we're going to finish up our derivative rules by learning a couple more derivative rules. We're going to do sine and cosine. So sine and cosine form a circle with their derivatives. Okay, so the derivative of sine is cosine of x. Okay, so I'm going to start with the sine x at the top here, and I'm going to draw an arrow going to the right. We'll go clockwise, and the derivative of sine is cosine. All right, derivative of cosine is negative sine. So we continue along our circle, and we get negative sine x. All right, and so if we go to the next step, taking the derivative of sine is cosine. So, but we have a negative in front. So this is that constant multiple rule. You take the negative out, you do the derivative, then you put the negative back in. So derivative sine is cosine, so the derivative of negative sine is negative cosine. Then the derivative of cosine is negative sine, so it's a negative times a negative, which is a positive sine. So they go in a circle like that. You just keep on going. And then eventually we're going to learn how to do an antiderivative, also called an indefinite integral. And we just go backwards along this circle to do that. All right, so let's do y equals 6x squared plus 5 cosine x. Y prime would be 12x, just using our power rule there. And then derivative of cosine, remember the 5, you can pull the 5 out. Take your derivative. Derivative of cosine is negative sine. And then multiply your 5 back in. So 12x, then I probably write this as minus 5. 5 times negative 1, sine x. And that's it. All right, so you have your homework down here, and you'll notice that I added something. You're going to prove that the derivative of cosine x is equal to negative sine x. And so I am going to prove for you the derivative of sine is equal to cosine, and then you're just going to follow along with that. Okay, so give me a minute to get set up here, and then we'll get going on that. All right, so find a blank space that you can write in, or grab a separate sheet of paper. And so we're going to do this proof. And anytime we're going to prove a derivative, we are going to use the definition of derivative, which is what we just got done learning about in our last unit. So to prove that this derivative is equal to this, we are going to set this up as the limit as h approaches 0. So it's f of x plus h. So that's sine of x plus h minus f of x, so minus sine x, all over h. Okay, and then we have to do some sort of algebra because this is currently in 0 over 0 form, and we need to find a way to simplify it. Okay, and so I say algebra is just a catch-all, but really we're doing pre-cal because what we need to do is we need to use the sine formula for a sum of angles. Okay, so this is a formula you learned in pre-cal last year. Probably not one you remember. I don't remember it off the top of my head very much every time. So I'm just going to jump over to Google here, and we're going to do sum of angles. Trig formula. That should give us what we need. All right, let's see. I'm going to go to images here. All right, this has what we need right here. So if you have sine of x plus y, which we have x plus h, but same idea, it translates into this. Sine x cosine y plus cosine x sine y. All right, so that is what we're going to translate our sine of x plus h into. All right, so we still have our limit. The limit as h approaches 0. So this is sine x cosine h plus cosine x sine h plus sine x. Nope, not plus, minus sine x. That's coming from this part right here. And then that's all over h. All right, so now I want to try to manipulate this so I could do something. All right, so that doesn't look like it really helped us, but it actually did. So like this term has a sine x, and our last term also has a sine x. So let's just rearrange it and put those terms next to each other. Sine x cosine h minus sine x plus cosine x sine h all over h. All right, and so what that allows us to do is if we just group these first two terms together, though they both have a sine x, and I can factor out a sine x from those two terms. So the limit as h approaches 0 of sine x multiplied by, so we'll have a cosine h left from there, minus 1 left from there. All right, and then I'm also going to split this limit up into two limits now at this plus sign. So this is all going to be over h, and then my new limit plus the limit as h approaches 0 of cosine x sine h divided by h. Okay, and we've seen this happen with limits before, especially with our definition of derivative, that the variable is an h. So this sine x, we can treat that like it's a constant because it has an x on the inside, not an h. So it is not affected by this variable right here. So we can just pull the constant out. So we're going to pull a sine x out of this limit. So it'll be sine x multiplied by the limit as h approaches 0 of cosine h minus 1 all over h. And then this one, same thing with the cosine x. You can pull the cosine x out times the limit as h approaches 0 of sine h over h. All right, and hopefully you recognize these two limits. These are special. These are ones you should have memorized. Okay, this limit of cosine of h minus 1 over h, we might have written it where the numerator was backwards, 1 minus cosine h over h instead, but that actually doesn't matter. I could have just taken out a negative from the top and it would switch them. It doesn't matter because this limit is equal to 0. So we have sine x multiplied by 0, and then over here, this limit should be even more familiar to you because we see it more often. Limit as h approaches 0, sine h over h is equal to 1. So the 0 cancels out that first term, and we are left with cosine x. And that's what we had to prove. So we draw a little box that says that we have proven what we set out to prove, and we're done. So you should be able to follow that blueprint to do your derivative of cosine x proof is equal to negative sine x. So hopefully that goes well for you.